So this is the third lecture of sugar. I'm going to continue with the cyclization. Just to review what we just talked about. The glucose sugar, even though we draw it in a straight chain, really don't exist that way, but you're going to learn to draw it in a pre-cyclized form like this. And then when it cyclizes, notice the carbon that used to be carbonyl is now a COH. So you have one COH, COH, and one OR on the same carbon, which is a definition of hemiacetal. So it forms a cyclic hemiacetal, which, by the way, in sugars is pretty stable. It doesn't automatically open up again. So because we're producing a chiral center, when this happens, you have a choice of OH being up or down. And so this, when the OH is up, which is on the same side as the CH2OH, we call that beta. The one where CH2OH and OH are on the opposite side is called alpha, right? And both anomers exist. Now, what you need to also learn how to do is draw these. This isn't a Hallworth projection, but you also need to be able to draw in chair conformation. All right, so I'm going to put the beta D, and look at the name, glucopyranose. All right, so the pyranose is the name referring to a cyclized 6-member ring. And if you see a name called a furanose, that's referring to a 5-member ring. All right. So notice how the name changed from glucose. It's not just glucose, it's glucopyranose to indicate that you're talking about cyclized version of glucose. All right. So to draw chair conformation, I want to just review how you did this. Remember, you draw like parallel lines like this, another parallel lines, and then you draw the last set of parallel lines. So there should be 3 sets of parallel lines, here and here, here and here, and here and here. Now what you're going to do is you're going to put the oxygen in the back corner. All right, and when you draw the parallel lines, you want to draw to the right and down, and that's the convention that the sugar is drawn in. All right, so this is your chair conformation, and what you're going to do is, this is the anomeric carbon. All right, that's the C1 right here. And starting from that carbon, you're going to draw all your axials. All right, so axial here is going to be down, here is going to be up, down. Remember, it takes turn, up, down. Those are your axials. All right, and then you're going to draw your equatorials in each of the carbon. And if you already have a down axial, then your equatorial is going to be pointing up, which means that this is going to be pointing down, this is going to be pointing up, this is going to be pointing down, and this is going to be pointing up. Those are your equatorials. Now, when you draw the beta D glucopyranose, you'll see that, for example, C1, OH is up, so it's in this position, the equatorial. And in C2, OH is down, and in this, that would be still equatorial. You'll notice when you draw in the chair conformation for glucose, the OHs are all in the equatorial position, and the last CH2OH is also in the equatorial position. This is the beta D glucopyranose. All right. So it should make sense why glucose is the most prevalent monosaccharide in nature, because look how stable, you know that the equatorial is more stable than axial. So OHs are occupying all the equatorial positions. Okay, so the blank spots that are left blank are the hydrogens. All right, so the only difference between that and the alpha D-glucopyranose is that the OH on the C1 is not up but down. So you could draw the same exact thing. And you're going to have the OH down this time, and then all the other OHs occupy the equatorial position. And that would be the alpha D-glucopyranose. All right. A lot of times this would be called alpha anomer, and it would be diastereomer of the beta anomer. Okay, because the only difference is at C1, the OH is up or down, so the relationship of the alpha D-glucopyranose and beta D-glucopyranose would be that they're diastereomers. All right. So in your book, they also go through how this cyclization of furanose looks like with fructose. So take a look at that. It's much simpler than 6-member ring, so I'm going to expect you to go over that on your own so that you can see what fructose looks like in a cyclized compound. So after doing this, you should be able to do the same kind of drawing with the galactose and show me in a chair conformation or a Haworth projection. I'll be accepting either one, what a cyclic hemiacetal would look like, and then also be able to do 24.9 and 24.10 on your own before you come to the lecture. All right. Now, the next topic that I want to go over is something called muta rotation, and that's in the next handout. And what you see in there is, as the name indicates, muta rotation. Mutate means changing, and the optical rotation is what the rotation is referring to. All right, so what happens in laboratory is that if you have 100% pure alpha D-glucopyranose, you'll see that the melting point of that compound is 146, and the optical rotation is positive 112 degrees. On the other hand, if you have 100% of beta D-glucopyranose, the melting point is slightly higher at 150 degrees, and the optical rotation is only at 18.7 degrees rather than 112. So they have different physical properties. But the strange thing happens is that when I get in a 2 different beaker, let's say I have 100% of the alpha D-glucopyranose and dissolve in water and let it sit for a period of time. Okay, so that's in one beaker, so imagine that. And at another beaker, I start out with 100% of beta D-glucopyranose, dissolve in water, and then let that sit over a period of time. What happens is that both over time will no longer stay at the optical rotation that it started with, but both will equilibrate to an optical rotation of 52.6 degrees. All right, both of them. It doesn't matter what you started with. Okay, so that's what the mutation rotation is referring to. Is the rotation is mutating over time. Okay, so what is this phenomenon and why does this happen? All right, so that's got to do with the equilibrium that is shown here, right? So you know that hemiacetals don't stay just hemiacetal, but it's an equilibrium process in which this cyclized version could go back to the straight chain for either one of the diastereomers. All right. So that is what's happening in water. So at any one time, whenever you have the glucose in water, what's happening is that you have cyclized form to start with, but at any instant is opening and then closing, opening and closing. So, okay, so let me show you with the model. So we have this cyclized form. And right now what's happening is this anomeric carbon is this a carbon that's got the OH and the OR. That's opening up and closing, opening up and closing. All right. So once it opens, then it has chance to close, open and close again. But how do you know which way is it going to close, with the OH down or up? So it happens in such that the 52.6 is really referring to a mixture of both the alpha and the beta form, and the mixture is 36 of the alpha to 64 of the beta form. All right, so we have slightly about 2 to 1 ratio of the beta to an alpha, but you have a mixture. So in other words, that optical rotation is reflecting this mixture no matter what you started with, and at any one time you have an open form of glucose, which is about 0.02%. All right, so after you equilibrate it, you have about 36% of this, and then 64% of this, and very, very minute amount of the open form, because it is continuously opening and closing, but it equilibrates to 64 to 36. All right, why not 50-50 mixture, right? The reason for that, can you guess, is the structure of the beta being slightly more stable than the alpha form. Notice where the OH is an equatorial position compared to the OH being axial position. But why not then 100% beta? That's because it's not that much more stable. It's slightly more stable, so that the equilibrium mixture is reflecting that stability of, and that's why you have a mixture, slightly more of the beta form than the alpha form. All right. So you should be able to answer questions like this. Will the following compounds mutarotate? You're going to have to take a look at the cyclized form of the sugars in each one of these, and ask yourself at the anomeric carbon, is it a hemiacetal or not? Because if it's a hemiacetal, then it's going to open up and close, and open up and close. But if it's not at the hemiacetal form, so in other words, at the anomeric carbon, if you have an acetal version, not a hemiacetal, remember acetals are a lot more stable, that's not going to be able to open up and close. So acetals are going to be fixed in rotation, and it's not going to mutarotate. So take a look at these 4 sugars, the structure of it in your book, and ask yourself which of these will mutarotate and which one will not. All right, the answer for that, you should be able to figure that out based on that structure. All right, and finally, after this lecture, you should be able to do 24.1.2a, 24.1.6, 1.7, and 1.8, and that concludes this lecture.